In this video, we will be looking at how to find the slope of a tangent line. So before we get into that, a reminder that a secant line is formed by 2 points on a curve, and then we can find the slope of that secant line using y2 minus y1 over x2 minus x1. So change in y over change in x. So this here, if this is 1 point, this is another point, this would be our secant line, and we have no problem calculating that slope. Now, for a tangent line, we know a tangent line will only pass through 1 point. So let's take this point here. My tangent line will follow the direction of the curve at that specific instant in time. So let's say this is the tangent line. Now, how can we find the slope of a tangent line if we only have 1 point? Let's call this point P. Well, I need 2 points to find the slope. So let's say I take this point that was on the secant line, but what if this point slowly got closer and closer and closer to point P? If we can find the slope of point P, and let's call this point Q, but we want the distance between P and Q, that horizontal distance, that x value, the distance between the x's, to be as close to 0 as possible. So let's call that horizontal distance h. And I'm going to say point P is located at A for the x value, and then F at A for the y value. And point Q is A plus h. H being that horizontal distance. And the y coordinate would be F at A plus h. And now we have 2 points, so we can use our slope formula. But I want h to be as close to 0 as possible. So that's where limits come into play. The slope of the tangent will be the limit as h approaches 0 of y2 minus y1, so f at a plus h minus f at a, over x2 minus x1, so a plus h minus a. Well, we should notice that the a's cancel out. So here is our slope of a tangent. The limit as h approaches 0 of f at a plus h minus f at a all over h. And this is called your difference quotient. And again, that a value would represent the point where we specifically want the slope of the tangent. So let's try out this first example. Given f at x equals x squared, determine the slope of the tangent to the parabola at the point 3, 9. So the point 3, 9 is our point P. So I'm just going to rewrite it here. Okay, so that would be f at 3 is 9. And then point Q, well, I need f at 3 plus h. Okay, so I'm going to replace x with 3 plus h, so 3 plus h squared, and I'm just going to clean that up. So I'm going to apply my distributive property. Remember, this means 3 plus h times 3 plus h, so that'll be 3 times 3 is 9, plus 3h plus another 3h, so that's 6 h's in total, and then plus h squared. There we are. Now here's my y2, here's my y1, and then it'll all be over h. So the slope of the tangent is equal to the limit as h approaches 0 of 9 plus 6h plus h squared minus 9 all over h. So technically in that denominator it would have been 3 plus h minus 3 if you're using the slope formula, but the 3's would cancel out. And that's why we're left with this. And now let's see what happens. Well, 9 minus 9 is 0. So those are gone. And I'm just left with 6h plus h squared in my denominator. Now I know I can't just sub in 0 for h, because that will give me that indeterminate form of 0 over 0. But I do notice in what's left of my numerator, both of these terms have an h common. So I'm going to common factor out an h, so that I have 6 plus h all over h. And then h divided by h is 1. So we're just left with evaluating the limit as h approaches 0 of 6 plus h. And now I have no problem substituting 0 in for h. And we get 6 plus 0, so 6. There's the slope of our tangent line. And now that we have the slope of the tangent line, we have no problem finding the equation of the tangent line because that's just y equals mx plus b. Y equals, our slope is 6, so 6x plus b. And we know the point 39 exists on this tangent line because the tangent line is passing through this specific point on the parabola. So 9 equals 6 times 3 plus b. 9 equals 18 plus b. And when we bring that 18 over, 9 minus 18 is negative 9. So the equation of our tangent line is y equals 6x minus 9. There we are. Let's try another parabola that has a little bit more involved. Given the function g of x equals negative x squared plus 4x plus 1, determine the slope of the tangent to the curve at the point determined by x equals 3. Okay, well, I need to know what f at 3 is. So negative 3 squared plus 4 times 3 plus 1. That's going to be negative 9 plus 12 plus 1, which is 4. And I also need to know what f at 3 plus h is. So we'll have negative 3 plus h squared plus 4 times 3 plus h plus 1. And I can do this all in one go in that difference quotient. I like to clean it up on the side just so that I don't have to write the fraction and the limit over and over again. So negative, and then my distributive property, so 9 plus 3h plus 3h plus h squared. Distribute the 4 in, so plus 12 plus 4h plus 1. Distribute that negative in, negative 9 minus 6h minus h squared plus, well, that's 13 plus 4h. And finally, I have negative h squared, I have negative 2h, and I have plus 4. And now I'm ready for my difference quotient. So the slope of the tangent line will equal the limit as h approaches 0 of y2 minus y1. So negative x squared minus 2h plus 4 minus 4 all over x2 minus x1, but 3 plus h minus 3 would just be h. And then let's see what happens. Well, 4 minus 4 is 0, which is great because that'll allow us to common factor out an h. And I know normally we would factor out a negative h, but I only need the h to cancel out, so I don't really worry about getting that full GCF. H's cancel out, and we're evaluating the limit as h approaches 0 of negative h minus 2. And now we have no problem substituting 0 in for h. So negative 0 minus 2 is just negative 2. Now we can find the equation of that tangent line again. So y equals negative 2x plus b, and our point is 3, 4. 4 equals negative 2 times 3 plus b. Negative 2 times 3 is negative 6, and when it moves over, we'll have 4 plus 6, which is 10. So here's the equation of this specific tangent line. Let's move on to a different type of function. Let's determine the slope of the tangent to the curve h of x equals 3x plus 6 over x, so a rational function, at the point p 2, 6. Now, if it bothers you that our function is h of x and h is the horizontal distance, we can always use a different variable for h and do the limit as, let's say, a approaches 0, or d for distance approaches 0. So we can try that for this one because it really doesn't matter what variable we use for that horizontal distance. So I'm going to start with h at 2. Well, we're already told that's 6. And now I'll do h at 2 plus d instead of 2 plus h. And I get 3 times 2 plus d plus 6 all over 2 plus d. And I have a little bit I can clean up here. 6 plus 3d plus 6 over 2 plus d, which is 12 plus 3d over 2 plus d. And now let's go ahead and use that difference quotient to get our slope. So the slope is the limit as h approaches 0 of y2 minus y1. So 12 plus 3d over 2 plus d minus 6 all over 2 plus d minus 2. So that's just going to be d. And oops, that should be as d approaches 0. Okay, so now I have a fraction within a fraction. And when I see this, I'm thinking I need a common denominator. So I'm going to put the 6 over 1. And if I just multiply the negative 6 by 2 plus d, top and bottom, I'll get that common denominator. And while I do that, I'll replace this main fraction line with division. So the slope of the tangent is equal to the limit as d approaches 0 of 12 plus 3d minus 6 times 2 plus d all over that common denominator. And that'll be divided by d. Now it looks a little better because I don't have a fraction within a fraction. And now it's time to clean up. The limit as d approaches 0 of 12 plus 3d minus 12 minus 6d, make sure you're distributing the negative in, all over 2 plus d. And instead of dividing by d, thinking about fraction division, we turn it into multiplication by the reciprocal. All right, a little bit more cleaning. 12 minus 12 is 0, fantastic. And I'll collect my like terms in the numerator, 3d minus 6d, so negative 3d over 2 plus d times 1 over d. And now these d's cancel out because everything was attached by multiplication. It was this denominator times d and then negative 3d times 1, so the d's cancel out nicely here. And we're left with the limit as d approaches 0 of negative 3 over 2 plus d. And now I have no issues with substituting 0 in for d. And we're left with negative 3 over 2 plus 0, which gives us a slope of negative 3 over 2 for this specific tangent line. And that's how we would approach a rational function with that common denominator. Let's try a square root function now. So we want to determine the equation of the tangent line at x equals 9 on the graph of f at x equals the square root of x. So first, let's figure out f at 9. F at 9 is the square root of 9, which is just 3. And I need f at 9 plus h, which is the square root of 9 plus h. So I can't clean that up more than this. So now let's go to that difference quotient. The slope of the tangent will equal the limit as that horizontal distance approaches 0 of the square root of 9 plus h minus 3 all over h. Now I see a radical. That's making me think of the conjugate. So I'm going to multiply the numerator and the denominator by the conjugate of the numerator. So that'll be the square root of 9 plus h plus 3. And I'll do the same thing on the bottom. And now we get the limit as h approaches 0 of the square root of 9 plus h times itself is just going to be 9 plus h, and then negative 3 times 3 is negative 9. I know if I multiplied the outsides and the insides, they would cancel out, so I'm not worried about that. All over h times that conjugate. And I'm not worrying about distributing that h in because I'm hoping things will cancel out nicely. So 9 minus 9 is 0, great. So all we're left with in our numerator is h. And lucky for us, h divided by h, well, that cancels out as well. So now we're just left with the limit as h approaches 0 of 1 over that conjugate. And I have no issues now substituting 0 in for h. So 1 over the square root of 9 plus h plus 3, and h is 0. So the square root of 9 is 3, and 3 plus 3 is 6. So our slope is 1 over 6. And now we were asked for the full equation of the tangent line. So we have y equals 1 over 6x plus b, and our coordinate is 9, 3. So 3 equals 1 over 6 times 9 plus b. 9 over 6 is the same as 3 over 2 plus b. And when I bring it over, I'm going to get myself a common denominator. 3 over 1 is the same as 6 over 2 minus 3 over 2. And that's 3 over 2 for our y-intercept. So that leaves us with the equation as y equals 1 over 6x plus 3 over 2. And that's how we would approach a square root function with that conjugate. So just using our previous limits knowledge. And finally, determine the slope of the tangent to the graph of g of x equals x cubed at the point x equals 2. So let's start off by finding g at 2. That's going to be 2 cubed, which is 8. And g at 2 plus h, which is 2 plus h cubed. Now, we can, of course, apply distributive property here and write out 2 plus h 3 times and do our proper distribution, and then do our difference quotient like normal. But when I look at this as my y2 and this as my y1, and if I think about how I would subtract them, kind of looks like a difference of cubes here. And that might be a little bit more efficient, so I'm going to give it a try. But again, you could definitely go and distribute this. So the slope of the tangent line will be the limit as h approaches 0 of 2 plus h all cubed minus 8 all over h. I'll put a little reminder that a difference of cubes is a cubed minus b cubed equals a minus b, so the cube root of the two original terms, times a squared plus ab plus b squared. So when I look at this expression here, the cube root of 2 plus h cubed is just 2 plus h. So a is 2 plus h, and the cube root of 8 is 2. So now let's try this out. So a minus b, so 2 plus h minus 2, times 2 plus h squared for a, plus a times b, so 2 times 2 plus h, plus b squared, so 2 squared, which is 4, all over h. Well, this is really good because in this first bracket, 2 minus 2 is 0, so I'm just left with h. So I have h times that second bracket. Well, h divided by h is 1. So all we're left with is the limit as h approaches 0 of 2 plus h squared, which I'm not even going to bother cleaning up because I can substitute 0 in for h in my next step, plus 2 times 2 plus h plus 4. And now I'm going to do my substitution. So the slope is equal to 2 plus 0 squared plus 2 times 2 plus 0 plus 4. Well, that's going to be 2 squared is 4. 2 times 2 is 4 plus 4. We get a slope of 12. So this is me trying to be a little bit more efficient, avoid doing that distributive property, and I noticed there was a difference of cubes. But like I said, we could have definitely taken this 2 plus h cubed and expanded and simplified it. So if you were to do that, and you wanted to just check for yourself another way, you would have gotten h cubed plus 6h squared plus 12h plus 8 if you did it properly and carefully. And then you could have done this minus 8 all over h, and it would have worked out to the exact same thing. So there we are. That's how we find the slope of the tangent using the difference quotient. So we're creating two coordinates. Point P is the actual point that we're trying to find the slope of the tangent at, and point Q is this point that is h units away from the x value. And then we can use our knowledge of limits and see what the limit is as h approaches 0 of that slope formula. And there we are.